Hank, you can start sharing. And then I'm just watching the attendee list numbers. It's still going up a bit, so
Okay.
we'll wait a few minutes and then get started. It usually works.
Right. So Ashley takes care of the sharing.
You can share your screen.
Oh, hold on. Oh, wait a minute. I'm in the wrong window here. There we are. Share screen. I want PowerPoint slideshow. Share. There we are. Okay. Can you see it?
Perfect. Yep.
Okay.
Wait another minute for this. So it looks like people are still starting to join a bit, so that's good.
Yeah, I had my my PowerPoint screen up, so I didn't have the Zoom screen.
I know it's always all those buttons like to hide and everything. So
yeah.
Okay, I think we can go ahead and get started. So I just want to mention before we get started, we started off Beyond the Scope a little bit over a year ago now, it looks like. We started off every week. We switched to every other week at the start of the semester. And since everything's starting to ramp up a bit more and there's some nice content people can find online, we are going to be switching the schedule to monthly starting this summer. So it'll be fun to keep this going with new talks and everything, but we'll just be doing it once a month, probably at the end of the month. So just keep an eye out for the schedule to be hopefully coming up soon with that. For today's talk, we'll have Hank Killane give a talk about X-ray analysis in the TEM. He's one of our assistant directors here at CMAS. He takes care of a lot of the day-to-day research operations here. I think he pretty much runs around and does a lot of stuff on basically I think he touches almost all the microscopes as well as managing the Tech9 microscopes. So again, with these talks, we aim to keep them at least somewhat interactive. So if people have questions, feel free to post those during the talk. Q&A is the easiest way to do it. If you're having problems with that, you can also post things in the chat, and Ashley and I moderate those to try and help out. Okay, I'll give it over to Hank.
Okay. Thanks, Dan. So I'm going to talk a little bit about X-ray analysis in the TEM or STEM. More usually we're doing this in a STEM mode rather than TEM. So just as a brief introduction again, these are the instruments we have at CMAS. But what I'm going to be doing right now is focusing pretty much on these four, which are our TEMs that have EDX detectors in them. Our cryo microscopes do not have any EDX capabilities. So a little bit about myself. I was born in the UK, grew up in the Pittsburgh area, got my bachelor's from Drexel and master's from Cornell, spent some time at Xerox, and I came to OSU in 1982 and ran the campus electron optics facility then until 2012, when the facility changed into the CMAS facility. So during that 30-year period, I did TEM, I worked on SEMs, I did Auger, focused ion beam, X-ray diffraction. But since we changed into the CMAS facility and increased our staff members, I focused more on the TEM and the XRD, X-ray diffraction capabilities. So I have a number of activities outside of OSU, and I'm one of the ride leaders for Columbus Outdoor Pursuit. So I do some cycling, I do some swimming, and try to interact with my grandkids when I can see them. So to start, this is probably something you've all seen at this point. X-ray analysis here with an electron beam. Basically, you have an incoming electron that will ionize an atom. So in this case, they're showing a K-shell ionization. You knock a K-shell electron out of the atom, And now you have the atom in an excited state. So one of these electrons in an outer shell will drop down to fill that vacancy in the K shell, in this case. Because there's a difference in energy between these states, that excess energy is carried off in an X-ray or in an Auger electron. And these energy levels are characteristic for each element. So by looking at the energy of the X-ray, we can identify what element gave rise to that X-ray, and we can count the X-rays and determine how much of that element is present. Now, you may have seen pictures of these detectors sitting on microscopes. The detector unit looked almost as large sometimes as an SEM column, but you'd see these hanging on the sides of TEM columns as well. And they look very impressive, but the whole thing, this big unit on the side, is just holding a lot of liquid nitrogen, just a big doer. All the work actually got done down in the tip here. So you had here a detector crystal that was maintained at liquid nitrogen temperatures. And they would put a window in front of it to keep it from icing up since it was so cold. So this crystal was usually in the older detectors, was a 3 millimeter piece of silicon. So your X-ray would come in, and when it would enter, it would start ionizing the silicon and generating electron hole pairs. So with this bias, your holes would migrate to one end and your electrons to the other. And then what you would do is measure the number of hole pairs that were generated. And then from that, you could infer the X-ray energy. So basically, it would take 3.8 EV to generate one electron hole pair. So when you start getting down to some of the lighter elements where your X-rays are in the few hundred EV range, you're actually detecting only like, well, for carbon, it would be about 70, 75 electron hole pairs, which is pretty impressive when you think about how much you're having to amplify it to detect things. So this principle is the same between the SILI detectors, which are the older style, and the SDDs, which are the newer style. They're basically both just diodes that have been biased in the reverse direction, so that you should have no current flowing through the diode. And then when you get the hole pairs created, then you get a little pulse of current coming out. So the SDDs, the silicon drift detectors, don't look nearly as impressive on your column. You have a much smaller unit, and then all you have is a Peltier cooler. So instead of keeping the detector at liquid nitrogen temperatures, they're usually held somewhere around -30 to -50 degrees C. And the geometry is slightly different. It's the same principle inside, but the geometry is a little different. So here your X-ray is coming in from the top. You will usually have some sort of a window up at the top here. Your X-ray comes in, you generate your electron hole pairs, but now they're swept out with this charge potential distribution due to these biasing rings. And the capacitance of this detector is much, much lower than the SILI detectors. So as a result, they can run 10, 100, even 1,000 times faster than a SILI detector. You can get up to hundreds or even up to maybe 1 million counts per second coming out of an SDD, depending on how you set it up. But in any case, it's still, you're generating a certain amount of charge that is proportional to the X-ray energy. So in the front of the units, you will have usually some sort of a window. This was absolutely required for the SILI detectors because since they were maintained at liquid nitrogen temperatures, they would ice up very quickly when exposed to any kind of atmosphere. So the ultra-thin windows could be made of either well, the older windows were made of beryllium, Then they went to the ultra thin windows, which were made of a parylene film, a polymer film, with an aluminum coating to act as a light barrier. But they would have to be mounted on a frame to make them mechanically strong enough to resist the air pressure difference across the window whenever a chamber was vented. So you would sometimes pick up a little bit of silicon in your signal from this frame that held the window. Newer windows now are using silicon nitride. Some detectors have the silicon nitride applied directly to the surface of the detector, and others still use some sort of a silicon frame type device. So once you get the signal coming out, so you have, here's your detector, whether it's a SILI detector or an STD, you have your charge coming out, and then you have your preamplifier system. Now, coming out of the preamplifier system, you will see a signal that looks something like this. As each X-ray comes in, you will get a voltage step in your output, and then periodically that gets reset to 0. And the height of the step then is proportional to the X-ray energy. So that's how you detect and discern which energy you have. So in the old days, this would be run into a multi-channel analyzer. Now this is all built in on a card inside the computer. So once we have this, we're basically interested in determining how many atoms or how many of some material we have in our sample. So we have to know how many X-rays we're generating. Well, obviously, the higher the current, the more electrons you get, so you'll get more X-rays. So the number of X-rays generated is the product of the number of electrons times the number of atoms you have in your sample, times something known as the ionization cross-section, which is now the probability that that electron will ionize the atom. And then you have the fluorescent yield, which is the probability that that ionized atom actually emits an X-ray. It turns out that an ionized atom can de-excite by either emitting an X-ray or emitting something called an Auger electron to carry away that excess energy. And the probability of an X-ray plus the probability of an Auger equals 1. So they're alternative processes. But now that's what we generate. We don't detect all of those X-rays. So some of the X-rays will be absorbed within the sample. Your detector has a certain kind of response function. So it has a probability of detecting a particular X-ray. But then also the X-ray or the detector will not detect all the X-rays that come out of the sample. It cannot see anything that heads off in a different direction. So you have a limited solid angle, and that will also reduce the number of X-rays we detect. So looking at the ionization cross-section, in its simplest form, the ionization cross-section in the beta model will look something like this, where U is something known as the overvoltage. So E sub C is the ionization energy of that particular atom, and E0 is the electron energy coming in. So that ratio is usually known as U and is called the overvoltage. If you look at this plotted out now, you can see that at a very low overvoltage, you're not going to ionize the atom at all. Once you get to the critical energy, an overvoltage of 1, now you start being able to ionize the atom. It will peak at an overvoltage of around 3 to 4, and then gradually drop off with higher voltages. Now in SEMs, where you have a limited kV, they're usually top out at about 100 at 30 kV. You have to watch out for this overvoltage issue, because it's hard to get sometimes enough of an overvoltage to efficiently excite your atoms. And this also then causes major issues when you're trying to do quantification. So this is showing like 120 kV. But if you think of a 200 kV electron and a 10 kV ionization energy, which is roughly where copper is, it's at 9, you're already operating at an overvoltage of 20. So you don't have to worry about that so much when you're doing TEM or STEM EDX analysis. The fluorescent yield, which is the probability of actually generating an X-ray from that ionized atom, there are, again, a number of models. This is a very simple model, but it does a pretty good job. So if you plot this out, now this is atomic number on the x-axis and the fluorescent yield on the y-axis. So you can see that as you go down in atomic number, this yield drops off greatly. So at a Z of 30, you're right around 50%. You get down to sodium at a Z of 10, you're now down in the 3 to 4% range. And by the time you get down to carbon, roughly one ionization out of every 600 will actually produce an X-ray. So any kind of uncertainty in this fluorescent yield number will give you a huge uncertainty in your final result. What it will lead to are bias errors in your analysis. So you have to be very careful when you're quantifying for these light elements. Now, I mentioned that the detectors have their own efficiencies. So the SDD now is shown in this red curve, and the older silly detectors are shown in this blue curve. So this is a calculated efficiency. So at about 10 kV, what you notice is now the efficiency of an SDD starts going down. And that's because the X-ray has high enough energy, it is penetrating the thin detector and going right through it without interacting. However, at the lower voltages, if you can look carefully here, you see that the SDD has a higher efficiency than the silly detectors. So, and it also depends on the kind of window that you have in your system, since the window will also absorb particularly these low energy X-rays. So this is all pretty much common between TEM or STEM and SEMs. So what are the major differences? Well, obviously, as we mentioned, you have the higher KV, and this obviously changes the ionization cross-section. However, anytime you have an energetic X-ray being decelerated, you will be generating what's known as Bremstrallo. These are hard X-rays, and these X-rays will go all the way up to the energy of the primary beam. So these are generally created in the condenser system, hitting one of the condenser apertures. And since they will not be focused, they will excite other parts of your sample that are far away from the area where your beam actually is. So you will sometimes pick up copper from a TEM grid, support grid, that is far away from the area where your beam is actually pointed. You will generate high energy backscatters. So your sample will backscatter, and you can't use an electron trap like you do in an SEM because your detector is so close to the beam, and you don't have, can't make the magnet strong enough to deflect these backscattered electrons. The detector is much, much closer to the sample in TEM than in SEM. Many of the detectors here are like 50, 55 millimeters away from the sample, whereas the detectors in our TEMs are on the order of 5 millimeters away. Also, we now have an ill-defined geometry. In the SEM world, a sample is assumed for quantification purposes to be flat, homogeneous, and semi-infinite, basically a very thick sample. If you're looking at something other than that, then be very careful with your analysis. So a TEM sample, in order to get the electrons through it, is of necessity very thin. and can vary in thickness. Also, when they're so thin, they may be bent, and that can also affect the emission of X-rays. Also, since your detector now is so close to the sample, it actually subtends quite a large range of angles. So you don't have a nice fixed takeoff angle like you do in SEM. So absorption is a major issue in SEM, but it's less of an issue in TEM, but it does happen depending on the X-rays in the system you have. So you do have to be aware of these assumptions and these criteria that are affecting your analysis. So very schematically, what you have in a TEM is you have actually two pole pieces now instead of one like you do in an SEM. Your detector is right up tight against the pole pieces. You do have a little collimator here, but generally it isn't overly effective. So you have your X-rays coming out of the sample, and then you have your transmitted electrons and your diffracted or scattered electrons coming out. So now you do have an additional complicating factor in that you have an objective aperture sitting in your pole piece gap. Since platinum has a backscatter coefficient of like 70%, your scattered electrons can hit this aperture and backscatter right up into your detector and can flood your detector. So working with an objective aperture in the TEM is generally not recommended. So that was a sort of a schematic drawing. This is something a little bit more to scale. So you have your pole pieces, upper and lower. This is would be looking at the end of the sample rod sitting in here, and you can see how tight the quarters are. You have your objective aperture sitting here, and then you have a collimator, and your detector would be sitting roughly right about here. And one thing you notice is how large an angle it subtends. So we will often talk about the takeoff angle, but that's only to the midpoint of the detector. So the detector actually extends down below the plane of the sample. So one of the things that we have to do in order to get a decent signal is we will have to tilt the sample towards the detector so that the detector can see more of the sample and you don't get shadowing from the sides of your TEM sample rod. So you are limited a little bit in that respect. Now, the newer systems that are coming from Thermo Fisher have what are called the Super X detector system. So now these are the actual SDDs that are built into the column itself. And Thermo will put 4 SDDs all the way around your sample so that you can leave your sample in the horizontal plane. You don't have to tilt it. So you can get actually now quite a large solid angle out of this. And that's very important as we're trying to detect very, very small amounts of material. So the larger the solid angle, the less X-rays are heading off in some direction that you'll never detect. So you're detecting more of the generated X-rays. Because the system is so tight, you do have to worry about stray signal. Now, the early TEMs, you had tremendous problems with spurious X-rays or stray signals. Modern TEM or STEMs, this is much, much less of a problem. There are various issues that they have done to minimize contributions from the pole pieces and so on, and backscatters. However, you still run into issues with scattering within the sample. So many times, your sample is mounted on a copper grid. As you tilt the sample, the continuum generated within the sample can actually cause the grid to fluoresce. The high energy electrons coming in can scatter from your sample and go over and hit your support grid and so on. So you will often see some sort of a background signal. If you have a copper grid, you'll see copper, or you can always choose a different grid material, gold or titanium or something like that. So you tend to choose a grid material that is will not interfere with the type of analysis that you're trying to do. So you do pick up some stray signal, but it's not nearly as bad as it used to be. So with all this, why do we bother doing TEM EDX analysis? Well, the major reason is resolution. In the SEM, your resolution is usually on the order of microns, a few microns. And that is limited by the scattering of the electron beam within the sample. So it doesn't matter whether you have a 1 nanometer, a 10 nanometer, or even a 100 nanometer beam, diameter beam. The beam diameter is not going to limit your resolution, it's the scattering. When we go to TEM or STEM, now we are working with a thin film. You still get some scattering, but as we increase our voltage from 100 to 300 kV, you can see that the scattering is much more limited. So now this scattering is small enough that we actually have to think about our beam diameter, which affects our resolution. So our beam comes in, it will have a certain diameter on the sample. But also, particularly in STEM, we have a certain convergence angle. So as the beam propagates through, it's going to get wider below this midpoint here, this focus point. And then also, on top of that, you will get some scattering of the electrons as they go through. So they will broaden this a bit more. Now, you can do a number of calculations. You can do Monte Carlo and so on, calculations to estimate that broadening. But as an easy approximation that you can work out on your little pocket calculator, the Goldstein equation does a very good job of estimating what your resolution is going to be, your spatial resolution, where Z is your atomic number, E0 is your beam energy, N is the number of atoms that you're scattering from, and T to the 3/2 is your thickness. So this does actually a pretty good job in estimating your beam broadening. This is the broadening due to the scattering, not due to the convergence angle or anything like that. So we can get good resolution. Now we need to start quantifying our data. So you've gone through, you've collected a spectrum. So you go through, you identify your peaks, and you always need to do, when you're doing your qualitative analysis, do a reality check. The automatic peak ID routines have improved dramatically over the past years, but still in many cases, they may misidentify a peak. The people at NIST have estimated that 3 to 5% of the time, they will give you a misidentification. So you do want to be careful about that. So once you've identified all your peaks, now you need to get the peak intensities by removing any background and unwrapping any overlapped peaks. In TEM, we use a different quantification method than in the SEM. In SEM, it's primarily ZAF or maybe Phi-Rho-Z. In TEM, we're usually using either the Cliff-Lorimer or the Zeta Factor methods, with the Cliff-Lorimer being the most common. And particularly with Cliff-Lorimer, you may have to modify your results with some absorption corrections. So the Cliff-Lorimer equation will describe relative concentrations. And it gives, of course, it gives you then only, since it's ratios, it gives you only n-1 equations for n elements. So that means that the necessary equation, last equation to solve the matrix, is that the sum of your concentrations equals 1. So you always have 100% of the material. But this equation completely neglects any absorption and fluorescence. So it's exactly valid only in the thin film limit, of course, at a thickness of 0, where you don't have any sample. In reality, we will state that the thin film criterion is met if you have less than about 5% absorption. That's kind of our rule of thumb. So the Cliff-Lorimer equation is a straight sensitivity factor calculation where you have your peak intensities. You take the ratio of those times a K factor or some sort of sensitivity factor. And then that gives you the ratio of the concentrations, generally done in weight percent. So these are relative sensitivity factors. And when you see them tabulated, they will be reported with respect to another element. And it's usually a common element. Most of the time, you will see them shown relative to silicon in the tables. Some people doing experimental work may use other kind of reference elements. So if they are reported, they will be reported with respect to silicon. So as you're doing your calculations, you can then easily calculate the relative sensitivity factors for any two elements in the table. So since you do have to sometimes think about absorption and fluorescence, you do need to know that your intensities will vary with thickness, because you do have some absorption and fluorescence. And you can calculate at what point you violate what we call our thin film limit. Now, here is an example taken on an old detector of a nickel aluminide sample. And this is really a pathologically bad case. The aluminum signal is very, very strongly absorbed. So you are out of the thin film criterion very quickly. So this is going thicker and thicker into my sample, and you can see how the aluminum to nickel ratio drops off very quickly. So you can calibrate this and calibrate that to thickness if you need to. The other method that's used is known as the Zeta Factor. And this is actually giving you a relationship of your X-ray intensity based on your dose. So you're getting a sensitivity per incident electron. So this is a much more absolute measurement. But it does require that you be able to measure your beam current very precisely. So most of the TEMs do not have built-in Faraday cups where you can measure that easily. Some of the EELS spectrometers enable you to do that, but it's something that's difficult to get in most of TEMs. It also requires that you pay very careful geometry to the careful attention to the geometry of the system, because as you change the tilt, you're changing the view of your sample that the detector has. So you'll get more efficient collection, which will then change the Zeta Factor. The edges of the sample rod that hold your sample in place are elevated above the sample, so they will shadow the X-ray detector from your sample. So as you tilt, this geometry will change. Or even if you are looking at a different point on your sample, that can also affect the efficiency of collection, which also can affect the Zeta Factor. So the Zeta Factor is a very good way of doing it, but it requires very careful attention to your acquisition conditions. So the Cliff-Lorimer has problems with the absorption correction. The Zeta Factor has issues with the geometry that you're working with. So they are both very good techniques, but each has its own drawbacks. So I mentioned that we're trying to get the maximum solid angle possible in our system. And we want to get a large number of counts because our data is described by the Poisson distribution. And here our standard deviation goes as the square root of the number of counts. So our signal to noise, which would be the intensity divided by the standard deviation, will only improve as the square root of the number of counts. Now, we also have a background here, and that will also have a Poisson distribution. So we have to do confidence testing to ensure that if we say that an element is present or is visible, that that the peak is beyond the uncertainty in the background. So basically, we want lots of counts to make sure that our peak intensity is at least 3 times the square root of the background intensity. And then we can say with 99.7 confidence that that peak exists and that element is in our sample. Basically, we want lots of counts. So we want a high beam current. We want hopefully a lot of the atoms in our sample. And we want a good geometrical collection efficiency, i.e. a large solid angle. And especially when we get down to having just a few atoms in the material, that's when we have to really be careful about saying that whether we have it or not. We want that large solid angle. Now, these days, pretty much all of our EDX work is being done in the STEM mode, which is scanning transmission electron microscopy. So instead of having a large beam striking our sample, we are going to a fine probe that we raster across the sample. So in a STEM image, we would scan the beam across in an XY direction and record the intensity. But as the beam sits on a pixel, it's also generating X-rays. So if we have our X-ray detector running, then we can collect X-ray counts at each particular pixel. So we now have a position-sensitive X-ray map that we're getting. And we produce something known as a data cube, where we have our XY coordinates, we'll have our intensity as one of these layers, and then we can have our energy in this direction and have a full spectrum associated with each pixel. So I have a couple of examples here of this type of work. So this is a metal matrix composite of aluminum and boron carbide. Now this is at a relatively low magnification. So this particular image is a TEM, not a STEM image. And the nice thing here is I can also come in here and do diffraction analysis to help identify my phases. So I went into STEM mode and focused on a smaller area of this sample, this area, which is now shown in this image. And then from this image, I collected a spectrum image from this rectangle here. And as we look at it, we see that I've got silicon and aluminum and my boron carbide up here. Now, this is pretty close to what you could do in an SEM. You see that I've got a 2-micron scale bar here. But if you look closely, right here at this interface, we've got a high nickel signal. And this is beyond the resolution limit that you would pick up in an SEM. Another example here that we've done in conjunction with the Byrd Polar Research Center, and this sample is from Paolo Gabrielli's research work. So this was a particle pulled out of a glacier and in the Antarctic. And you can see that it's very heterogeneous. And we're down here in the few nanometer range. So we started looking at this and we did an EDX map of this particular particle. So here's my acquired image. And then I started separating out the elemental signal. So you can see that this area is very high in silicon. And it turns out it was also high in oxygen. So it's not surprising. We have silicates in our nanoparticles. But you see there are bright spots, and I noticed that this area doesn't really have any silicon in it. So what is this? It turns out that it's very rich in iron. So that's an iron oxide, because this also showed very strong oxygen. And you see that many of these bright spots in the silica matrix, are made of iron. So it has a lot of iron dust in this, iron nanoparticles. But not all the particles light up. And in particular, this one, oh, yes. So I can now, having a spectrum image, I can come in here, I can select these pixels in my image and come up with a very nice spectrum showing this high iron signal coming out from that area. So moving on, it turns out that this bright spot, which was scattering strongly, was not an iron particle, but it was high in mercury and sulfur. And when we came in and looked at the X-ray spectrum from just those pixels, again, it showed a signal in mercury and a signal in sulfur. So again, this was a mercury sulfide particle that was embedded in there. And with this combination of materials, they deduced that this was some sort of a volcanic ash particle that had drifted into the glacier. Now, extending this even further, in our Titan microscopes, we can actually get to atomic resolution. And this is obviously something you can't quite get to in the SEM. So here is what's called a HADF STEM image, so a high resolution, high angle annular dark field image. And this little area here is shown in this EDX map. So the signals that were collected show all these different elements in this particular alloy. So you see the nickel, and then here's the aluminum signal. And if we take the nickel and aluminum and add them together, we can now get this type of a signal. We can then add in the titanium locations and produce this signal. We can add in the tantalum locations and get the sum of those. And we can even add in exactly where the cobalt is sitting and come up with that. So these are just a few examples of some of the kind of work we can do in TEM and STEM at various higher spatial resolutions than you can do in the SEM. And I will then, ending with that, I'll invite you to feel free to contact us if you have any questions. We're more than happy to talk about any of these techniques, and often at some length, and give you information. And once again, please stay connected. And with that, I will open it up for any questions that anyone might have.
If anyone has any questions, yeah, go ahead and post those in the Q&A. Is the easiest way to do it. Also, if you want to have more in-depth questions, chat, you can raise your hand as well. That works for a nice discussion. Or as Hank said, you can always contact him or any of the CMAS staff, and we can have some great discussions after that.